In this video, we're going to talk about transformations of random variables. So we've already seen really how to calculate the PDF of y when y is some function of x. In general, if we have a one-to-one function, so if the function of x is invertible, we can figure out a rule depending on whether or not the function is actually increasing or if it's decreasing. So let's do the case where it's increasing. So we've done this before where we said we want the distribution function of y, so we just do it by definition, probability that capital Y is less than or equal to little y. Put in what y is equal to. Since k is increasing, when we do the inverse on both sides, it doesn't flip the inequality. So we have x is less than or equal to k inverse of y. So for example, like if we had x cubed here, we would just have x is less than the cube root of y, right? Because the cube root is an increasing function, so we don't have to worry about flipping the inequality there. So this, of course, is now in the form of the distribution function for x evaluated at the k inverse function. Now to find the PDF for y, we differentiate. Chain rule says this is what the derivative would be, right? Derivative of the outside, leaving the inside alone, times the derivative of the inside. And that would give us a formula for what we want. Simplify it a little bit more, of course, this is the derivative of the cumulative distribution function, which gives us the PDF for x. So if you've got an increasing one-to-one function, we could just evaluate the PDF for y by using this formula. Again, we've done this before, we just didn't bother writing out a formula for it because it's just easier to remember the definition and go through it, at least in my opinion, so you don't have to try to memorize an extra formula. Let's do the case where it's decreasing. Same idea, write down the definition of the distribution function, plug in the function of x. Now since k is decreasing, when we apply k inverse to both sides, it does flip the inequality. To get this into the form of the distribution function for x, we need to do 1 minus the probability, right? The probability of the complement. And now we have 1 minus the distribution function of x evaluated at the k inverse function. And now, just like we did in the previous slide and like we've done probably 50 times before, take the derivative of the cumulative distribution to find the probability density function. Now, when we do this, the derivative of the outside function, well, the 1 goes away, but we still have this negative out in front. So we get negative f prime times the evaluated at the inverse function times the derivative of the inverse function. And again, we recognize that capital F prime is little f. Now, notice it kind of looked like the previous function, or the previous formula that we have, except that we have a negative sign in front. But remember, if k is decreasing, that tells us something about the derivative of k and also k inverse. Because if k is decreasing, then so is k inverse, which means its derivative will be negative, but we're taking the negative of it. So we can write this last line as the PDF evaluated at the inverse function times the absolute value of the derivative of the inverse function. And this also holds when k is increasing, because if k is increasing, the absolute value is just itself, because the derivative will be positive. Let's do a couple of examples here, just showing you how the formula works. Let's take the PDF of 2x. Let's let y equal negative 2 log x. So if we look at the inverse function, doing the inverse x as a function of y, we would divide both sides by negative 2 and then do e to that power. So we get x as e to the negative y over 2. So let's use the formula now. Here's the formula. We already have the PDF and we have the inverse function. So the PDF is 2 times plugging in the inverse function for x, and then the derivative of the inverse function will be a negative e to the negative y over 2. So we do the absolute value of that, and then of course the absolute value kills the negative sign, and we just get e to the negative y. They tell us the support for x is 0 to 1, and of course as x goes towards 0 from the right, natural log of x goes to negative infinity, but of course we're multiplying by a negative, so we actually get y going off to infinity, and if x gets close to 1, natural log of x gets close to 0, So we have y is actually between 0 and infinity. So we see that this really is just an exponential distribution with theta equal to 1. Let's do one more example where we have an x squared. So let's let f of x equal 1 minus the absolute value of x, evaluated from -1, or it's not evaluated, with a support of -1 to 1, and y is equal to x squared. Now in this example, this is not invertible on this interval. This function is actually was referred to as 2 to 1, not 1 to 1, right? Because we know we have a nice parabola when we graph y equals x squared. It's not invertible. So it's probably just as easy to go back to the original way to do this. Go back to the definition, plug in your function. Now when we rewrite this equation, we get a double inequality. When we rewrite this inequality, we get a double inequality. And we can rewrite that as a difference of distribution functions. And then take your derivative now. So we take the derivative now by the chain rule. We get both of these pieces. Notice here we have a negative root y, but we had a negative out in front. So when we take the derivative, the negatives will make that into a positive. And then each of these are the PDFs. So now we can plug this in to the PDF. So we get 1 minus absolute value of root y times 1 over 2 root y. Same thing, except we have negative root y plugged in there. Notice that the negative root y absolute value is the same as the absolute value of root y. So we can actually combine things together, combine like terms, and get this 1 minus root y over root y. Since x is between -1 and 1, it's not too hard to see here that y has to go from 0 to 1. Anyway, this gives you a couple of examples of how you do transformations of random variables in terms of one variable. In the next video, we're going to do this for 2 variables and see how it will extend to more than 2 variables.